physicist. And today, we're going to talk about the fact that what goes up must come down, or gravity, but specifically gravity for relatively small things that are here on Earth. There's a lot to talk about with gravity, and it's far too much to talk about in just one video. But one of the things we think about a lot in physics, and that we kind of know intuitively from our own experience, is that when something comes up, it has to come down. And one of the things we know pretty well in physics is the speed at which it's going to come down. That's because everything on Earth is going to accelerate due to gravity at this rate, g. It's about 9.81 meters per second squared. This is a constant value. For any object of any size, any shape, any mass on Earth will have the same acceleration due to gravity. That means if I just drop something, I'm saying it shouldn't matter what I dropped, it should fall with the same acceleration. This is actually really important in physics. We use it all the time. We use this kind of gravity in one-dimensional kinematics when you have an object that you just drop. We use this concept in two-dimensional kinematics when you have something that's moving through the air. Maybe you shoot a person out of a cannon and they fly forward with some speed, but the thing that's making them accelerate is gravity, so they're slowing down and falling. We also use this all the time when we're talking about forces. For any object on Earth with mass, we're going to want to consider its weight force, which is always going to be the mass times the acceleration due to gravity, or g. Today, we're going to keep things nice and simple by replicating a classic experiment to show that there is indeed a constant acceleration due to gravity. Here's the classic experiment. Back in the 15 and 1600s, people were kind of like, does gravity depend on how big something is? Maybe if something's heavy, it'll fall faster? Like, that seems like it would make sense. And according to myth, this is probably not true, but it makes a good story. Galileo said, gravity doesn't depend on mass, and I can prove it. And so he went up to the top of the Leaning Tower of Pisa and he dropped two balls made of different material. And they fell and they hit the ground at the same time. Now, we are going to do our own version of this experiment. Of course, this is a really simple experiment, and there's some things it doesn't take into account. For example, in order for this to work, you need the balls to be the same shape, because otherwise they'll be affected by air resistance, and a wider, bigger thing will be slowed down more than something that's small and compact. So now we are going to step away from the PowerPoint and give this a try. So it seems intuitive that Galileo should be wrong. If I drop something heavier, it feels like it should fall faster. So let's try it out. I have with me two identical jars, one which is full of paper clips and one which is empty. I realize the empty one's a little hard to see. What we're gonna do is raise them up over my head so they have enough room to get started decently, drop them, and see if they're falling at the same rate or at different rates. If the rate at which they fall depends on the mass, then this one should hit the ground well before this one. If it doesn't, then they should go past the camera at the same time. Conveniently enough, the iPhone has a slow motion feature, which will let us actually see what's happening. Because if I just drop them at full speed, yeah, no idea. Well, so what happened? I started the two jars with the same initial velocity. In theory, nothing. I didn't try to throw them down, I tried to just drop them. Now we're doing an experiment in my office with two jars of paper clips, so this isn't going to be perfect. But we get the general idea that I didn't try to throw them down, I tried to just let them go. And in theory, I let them go with zero initial velocity downwards. So the only velocity they should have picked up, and therefore where their position is, should be dependent on the acceleration due to gravity. The amount of acceleration they're getting just from the Earth pulling them downwards. And if that value were dependent on mass, then this guy should have passed the camera before this guy. But that's not what we saw. What we saw was that they passed the camera at the same time. Now in principle, we could mess this up a little bit by getting things with a dramatically different size or shape. and dropping them, and see that actually, because of how air resistance works, it does matter what the shape of the object is. That's why I didn't really drop a cannonball and a feather like Galileo allegedly did. I dropped 2 identical jars. I actually tried to make that happen, and what I found was that because things will try to shift around to get the lowest cross-sectional area, it's actually pretty difficult to have the same mass but different shapes and actually get it to drop and not just rotate around so that you end up with a smaller cross-sectional area and the same basic dropping. So I don't have a video clip for that. But what I can say is that the mass of the object doesn't determine how fast it accelerates due to gravity. Just for fun, I wanted to mention one quick caveat. One time where the acceleration due to gravity is not constant. When we calculate the acceleration due to gravity, we make a lot of assumptions, and one of the assumptions we make is that everywhere on Earth is equivalent. But that's not really true. In particular, if you are at a higher elevation, you're not going to experience quite the same acceleration due to gravity. So the tree at the bottom of the mountain would have gravitational acceleration GA, that would be 9.81. The one halfway up the mountain, GB, would be a little different. GC on top of the mountain a little different, and GD in the hot air balloon would be even more different. In fact, it would actually matter for GD that it is partly in the air versus being on top of an even taller mountain. It turns out the density of the Earth is also a factor here. But for most applications, we can either treat G as constant, or maybe if we're being really tricksy, we might use the equation on the left. We might say that the acceleration due to gravity at some elevation h is equal to 9.81, the acceleration due to gravity at sea level, times the radius of the Earth divided by the radius of the Earth plus the height of where we are. And then that quantity squared. This just scales our acceleration due to gravity to account for the fact that we're at a different elevation or a different height. So today, we've talked a little bit about basic gravity, and the main thing we've done is we've actually tried the classic Galileo dropping things off the Leaning Tower of Pisa experiment, but with little tiny jars in my office. I hope that this has helped you get a better intuitive understanding for what the constant acceleration due to gravity means. And I also hope, as always, that you'll realize physics is not so scary.